Welcome to the Balancing Chemical Reactions screencast. When balancing chemical reactions, it's both an art and a science. The balancing portion of it is determining the correct coefficients for each molecule in the chemical reaction. Since we know the total number of molecules in a reaction are the same on both sides of the equation, we can balance these molecules by looking at the molecular formulas and their subscripts, keeping these intact, and then using whole numbers as coefficients to balance the equation. And we always have to use the lowest set of whole numbers. It's kind of a mouthful, so let's look at a couple of examples. Here's a correct example. This happens to be a balanced reaction. It has 4 atoms of iron here in a solid form. It has 3 diatomic molecules of oxygen as a gas, and it results in 2 of these molecules as a solid. When we add up all the atoms, we have 4 atoms of iron here, and we have 2 times, the 2 is the subscript, which yields 4 atoms of iron. We have 6 atoms of oxygen, and we have 2 times 3, 6 atoms of oxygen. And if we look all the way across the equation, we have 4 plus 6, which is 10 atoms total, and we have 2 times 2, which is 4, and 2 times 3, which is 6, which yields 10. So there's 10 atoms producing 10 atoms, which is a balanced equation. Here's a couple of incorrect examples. This example has whole numbers as coefficients. It balances, but these are not the lowest set of whole numbers. So we have to use the lowest set, which is these numbers up here. And then this set here is a fractional set, and it needs to be a whole number. Let's look at another example. Take a look at this equation briefly and see if you can find some way to balance it in your head just initially. And then we'll go on and try to balance it ourselves now. The equation is aluminum in a solid form reacts with sulfuric acid and yields aluminum sulfate and hydrogen gas. This is how the equation reads. Solid aluminum placed in a solution of sulfuric acid produces aluminum sulfate and hydrogen gas. As an aid to balancing this equation, I'm going to draw a little chart here. And this is a way to successfully balance all equations. Once you do this method a few times, you can start balancing these equations in your head in large part. Some difficult equations, larger equations, may require use of this chart again. So I'm going to take all of the atoms on the product side, put them in this chart, and then put all the atoms on the reactant side and put them on this side of the chart. We'll start with this ion, which is a sulfate ion. Note that we're going to treat this ion as a unit, and there's 3 of them. That's what this means here. There's 2 aluminums, and there's 2 hydrogens. On the left side, there's 1 aluminum, there are 2 hydrogens, and there is 1 sulfate ion. Now we look at each row here and we see that these atoms are not balanced, or this ion. We go across, they're not balanced, and we're going to use these blank cells to arrive at a balanced number. So let's move forward. First, I'm going to make an assumption. I'm going to say we have one of these. And I just go over to the most complex molecule and I say for ease that we have one of those. So if I have one of those, that results in the sulfate one times 3, which is 3. For the aluminum, it results in 1 times 2, which is 2. Now I'm going to change pens and go to the second step. I'm going to look on the left side of the equation. I'm going to say what's happening with this molecule. So I have an SO4 over here, and I need 3 of them. So I'm going to put a 3 here, and that gives me 3 here, and 3 times 2 is 6, so I need a 6 here total, and that gives me a 3 here. Next, I look at the aluminum, and I place a 2 there, and that gives me a 2 over here. And the last thing I have to do is balance a coefficient with the hydrogen. So I'm going to change pens. And since there's 3 times 2 yields 6 hydrogens, put a 3 here. That's the third step. And that yields 3. As I look at the rows, I have 3 plus 3 on this side. I have 2 plus 2 on this side. I have 6 on this side for hydrogen. And if I look at it in a nice, neat structure, typed, it looks like this. And if I do a check, I have 2 atoms balanced with 21 atoms, balanced with 17 atoms, balanced with 6 atoms. So 2 plus 21 is 23, and 17 plus 6 is 23. So it balances. I have the lowest set of whole numbers, and when I check any of the elements, they're the same on both sides of the equation. Let's do another example. Why don't you pause the screencast and take a look at this equation and see if you can figure it out using the method we just used. Then resume and we'll go through the solution. We have lead-2 nitrate in an aqueous solution reacting with potassium chromate, and it yields lead-2 chromate and potassium nitrate. It reads solutions of lead-2 nitrate and potassium chromate combine in reaction to produce solid lead-2 chromate and a solution of potassium nitrate. I diagram all of my elements in this table. I bring them down. I have 1 CR4, 1 PB, lead, and so on, all the way through. I go to the next step. I want to balance this equation. So I make an assumption with the most complex molecule. I say there's one of them. That yields 1 here. 1 CrO4 is 1. 1 PB is 1, so these both total 1. I go to the next step, which is the second step, and I'll get my blue pen out here. And since I have a 1 CrO4, I'm going to bring this across, and I'm going to say there's 1 as a coefficient here, which yields 1 here. And for the K2, I come down here, and that results in a 1 there as well. I look at the PB part of it, and I have to calculate that as well. 1 yields 1. So I'm going to put a PB there, and it yields 1. And for this product, this also yields 1 for that polyatomic ion there. And for the third step, let me get my green pen out. all I have to do is figure out what did I do with these last two. So the NO3, it looks like I need 2 of those because I have 2 right here. That's the subscript. So on this side, I need 2 of those. So I'm going to try a 2. I'm going to put 2 here. I'm going to check and see if the potassium balances. There's 2 of them on this side. 2 times 1 potassium atom yields 2. Then I check my numbers in the rows. 1 times 1 is 1 is equal to 1. 1 is equal to 1. 1 times 2 is equal to 2 times 1. 1 times 2 is equal to 2 times 1. And the reaction is balanced. Let's take a look at it in nice typed out form. And let's check our answer. It looks balanced, but we're going to count the total number of atoms. So for the total atoms, I have 9 atoms right here. 1 plus 3 is 4, times 2 is 8, plus 1 is 9. Using the same method, I have 7 atoms on this side. And on this side, I have CrO4, which is 1 plus 4, plus 1 times that is 6. So that's taken care of. And I have 2 times K, which is 2, plus another 2, plus 2 times O3, which is 6, yields 10. 9 plus 7 is 16. 6 plus 10 is 16. So the answer checks. Thank you for watching this screencast.